Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In the second part of the DSC series, we're going to look at the principles of heat flux and power compensation DSC, and see how DSC data are generated. Once you appreciate that, you'll be all set to really understand the technique and design the best experiments for your sample. So, settle in and let's make a start. We've already seen that a DSC measures the difference in power required to heat sample and reference materials between two temperatures. To raise temperature, a DSC supplies energy using a heater, which is called a furnace. And it is the furnace arrangement that determines how the instrument works. If there is one furnace heating both the sample and reference materials simultaneously, the instrument is called a Heat-Flux DSC. If there are two furnaces heating the sample and reference materials independently, the instrument is called a power compensation DSC. Although the data produced by either type of DSC are the same, difference in power as a function of temperature, there are subtle differences in how they generate those data. Think first about the sample and reference materials. The reference is usually an empty pan, made of aluminium for most pharmaceutical measurements. The sample, however, will vary from experiment to experiment, but is usually an organic solid encapsulated in an aluminium pan. The heat capacities of the sample and reference will then be different. The heat capacity, remember, is how much heat is required to raise the temperature of a material. The higher the heat capacity, the more energy is needed to raise the temperature. Some compounds have rather high heat capacities. Water is a good example, and that is why there's a very large heating element inside a typical kettle. A DSC needs to supply energy to the sample and reference to heat them in temperature. If the heat capacities of the sample and reference are the same, then the amount of energy needed to heat them will be identical. If, in the more likely case, the heat capacity of the sample is higher than that of the reference, the DSC will need to provide more energy to the sample than to the reference to keep them at the same temperature. In the case of power compensation instruments, it's easy to see how this is achieved. The sample and reference are each heated with separate furnaces, so the heat supplied can be varied to keep the materials increasing in temperature at the same rate. The difference in power is determined directly from the two furnaces. In the case of heat flux instruments, the situation is a little more complicated. As there's only one furnace, the energy being supplied to the sample and reference materials must be the same. But if their heat capacities are different, they will begin to rise in temperature at different rates. In the very first types of instruments, the sample and reference temperatures were measured with thermocouples, leading to a plot of difference in temperature as a function of instrument temperature. This type of analysis is called differential thermal analysis, or DTA. The only difference between DTA and a modern heat flux DSC is that in DSC the sample and reference are connected by a highly conducting metal and can thus exchange energy. This is where the term heat flux comes from. The energy will flow from the higher temperature side to the lower temperature side, and so has the effect of keeping the sample and reference materials at close to the same temperature. 3 measurements of temperature are made: that of the sample, the reference, and the instrument itself. From these values, it is possible to calculate the changes in heat needed to raise the temperatures of the sample and reference materials, although we won't go into the mathematics here. I have put a link to a very good textbook in the description if you really want to get into it. In any event, a DSC produces a plot of the difference in power supplied to the sample and reference as a function of temperature, and any phase transitions in the sample are shown as a deviation from baseline. But why does a change in the sample cause a deviation from baseline? To answer that, I think it helps to think about what the instrument needs to do in order to heat the sample and reference materials. I'll use a power compensation design to explain the principles, as I think it's a little easier to follow. But the basic principle applies to Heat-Flux DSCs too. At the start of an experiment, both sample and reference are at the same temperature. The instrument supplies heat from the furnaces in order to start to increase the temperature. If the heat capacities of the sample and reference materials are the same, and I know that's unlikely, but bear with me, and I'll come back to that in a bit, then they require the same amount of energy to be raised in temperature, and the difference in power being supplied by the furnaces will be zero. Hence, a DSC plot for a sample doing nothing against an inert reference of the same heat capacity will be a flat line, positioned at zero on the y-axis. Now let's think what will happen if the sample does something. And since a lot of pharmaceutical materials are crystalline solids, I will choose melting as an example. Melting means the bonds holding the crystal lattice together must be broken, and that requires energy, an endothermic process. The only thing supplying energy to the sample in a DSC is the furnace. So when the sample starts to melt, the energy being supplied starts to break the intermolecular bonds holding the crystal together. Because the energy is being used to break bonds, there is none left to raise the temperature of the sample, and so it will remain at a constant temperature. The reference, on the other hand, is inert, and so uses the energy it is being supplied to continue to rise in temperature. Thus, the difference in temperature between the sample and reference materials starts to increase. Remember, however, that the instrument is designed to increase the temperature of the sample and reference materials between two values at a constant rate. And while the sample is melting, it is clearly not doing that. The instrument therefore has to do something to get the temperature of the sample back to where it should be. And it does this by increasing the power being supplied by the furnace to drive the sample temperature back to that of the reference. I hope you can see, therefore, that while the sample is melting, the instrument is having to supply more power to the sample than to the reference, and so the difference in power is no longer zero. In fact, the extra energy being supplied to the sample should be exactly equal to the amount of energy needed to melt the sample, as we'll come back to in a bit. When we plot the DSC data for a sample that's melted, we see a peak, and the peak has come from the fact that the instrument has had to put more energy into the sample than to the reference. Incidentally, you might ask me, what happens when the sample undergoes a process that gives out heat, an exothermic process, like crystallization? The answer is that as the sample starts to undergo an exothermic process, the heat given out raises the temperature of the sample relative to the reference. In that case, the instrument reduces the heat being supplied by the furnace to drive the temperature of the sample back to where it should be. It does not increase the power being supplied to the reference, because that would have the effect of heating the materials up faster than is being programmed. In either case, endothermic or exothermic, a peak is generated in the DSC trace, because the sample furnace needs to supply more or less energy respectively to the sample than to the reference. The fact that we see peaks in a DSC trace every time the sample undergoes a phase transition is the reason that DSC is so popular. We can see all the physical changes that a sample undergoes. It's also why DSC can be hard to interpret, because one peak looks very much like another. I have lots of handy hints as to how you can interpret DSC traces, but those are coming up in a later lecture. First, I want to focus on what information we can get out of the data. I mentioned in the introductory video that the main things are transition temperatures, areas under curve, and information on heat capacity. So let's look at those in turn. Transition temperatures are easy. We can report the first deviation from baseline, an onset temperature, or the peak maximum, the maximum temperature. The only reason onset temperatures can be tricky is where peaks are overlapping, and it can be difficult to see where the second peak starts. Areas under the curve need a little more thought. In most DSC software, you can place markers at the start and end of a peak, and the software will calculate the area for you, reporting the total change in heat. Nothing odd in that, you might think. But you do need to think carefully about units. A DSC, remember, plots power as a function of temperature. Power is not the same as heat. They have different units, but many people seem to use the terms interchangeably. So, a good thing to do is to understand what they are and why they are different. In trying to find a way to help people understand these terms and the units, I managed to find what I believe is the only question in the English language that is also its own answer. The question is, what is the unit of power? And the answer is, what is the unit of power? Hopefully, that will help you to remember the unit of power. The same principle doesn't work so well for heat. What is the unit of heat? Joule is the unit of heat. So, you'll just need to remember that heat is measured in joules. As an aside, you might say to me that heat is measured in calories. And you'd not be wrong. Heat can indeed be measured in calories. It's just that in most of the world, and by that I mean outside of the US, we use metric units. And the metric unit of heat is the joule. I was once at a big international conference where a wonderful speaker, the late great Tom Hoflick, was taking questions after a very entertaining presentation. And he was asked, "You're presenting data in London. Why are your data in calories and not joules?" And he replied, "When they rename calorimetry joulerimetry, I will present my data in joules." That was a good answer. I will be presenting my data in joules. In any event, since power is measured in watts and heat is measured in joules, they must be different. Different but related, because 1 watt is 1 joule per second. In other words, power is the rate of change of heat. This is why the DSC measures power. The furnace supplies energy as heat in joules over a specific period of time, in seconds. So that means the y-axis of our DSC plot is power in watts or joules per second. To determine the area under a curve, we integrate the data. I already said that the area under the curve of a DSC trace can give us the change in heat. But hang on, integrating power, joules per second, with respect to temperature, in degrees centigrade, won't give us a value in joules. We need the x-axis to be plotted in time, in seconds. Handily though, because the instrument heats the sample at a constant heating rate, we can easily convert temperature to time. For instance, if the heating rate was 10 degrees centigrade per minute, then each increase in 10 degrees on the x-axis corresponds to 1 minute. When we use the DSC software to integrate the data for us, we should remember that it automatically converts the x-axis data to time in order to get the units correct. I say this because A, I'm a pedant, and B, if you ever decide to export DSC data and integrate them yourself, you'll need to remember to get the units correct. So, the area under the curve gives us the change in heat associated with the phase transition. This is very useful, especially if the sample has melted, because the heat of melting is a very characteristic value and helps us to assign a polymorphic form, as we'll look at towards the end of this video series. Now, melting is an endothermic process. That is, we must add energy to a material to get it to melt, because we must break the bonds holding it together. By definition then, endothermic changes in heat are given a positive sign, because we have added energy to our system, while exothermic changes are given a negative sign, because the system has lost or given out energy. Those of you still following might say to me, hold on a minute, Simon. You said the area under the peak on the DSC trace was the heat of melting, but the area value is negative, whereas it should be positive. And I would say, excellent, you are totally right. We have to remember when plotting DSC data that the instrument is plotting the difference in power needed to change the temperature of the sample and reference. And it can calculate this as sample minus reference or reference minus sample. Which is correct? Either. It's a difference value, so we can calculate it either way. And that is exactly what manufacturers of DSCs do. Some calculate sample minus reference, and some calculate reference minus sample. This doesn't really make a difference, except that the direction in which endothermic and exothermic events are plotted will change. Therefore, it's very important that we note on the DSC plot in which direction data are being shown. We do this with an arrow on the y-axis showing whether exothermic events are being plotted as positive values, exo up, or negative values, exo down. Without this information, interpreting DSC data can be very tricky. My instruments plot exo up, and so endothermic events such as melting are shown as downward peaks, as I have drawn. We just need to remember that because these negative peaks represent endothermic processes, we must report the area as a positive. Now, I said earlier that I assumed that the sample and reference materials had the same heat capacities. Can you see what the effect would be on the baseline position if the sample and reference materials did not have the same heat capacities? I shall give you a moment to think about that. Had a think. The answer is, if the heat capacity of the sample was higher than that of the reference, then it would require more power from the furnace to raise in temperature at the same rate. Thus, the difference in power is no longer zero, but will be proportional to the difference in heat capacities. And the baseline will shift either higher or lower depending on whether the instrument is plotting sample minus reference or reference minus sample. You can work that out for yourself later on. We use this effect to measure heat capacities. We measure the baseline shift for a sample with a known heat capacity, usually a sapphire crystal, and then the baseline shift for our material being tested. The ratio of the baseline shifts gives the heat capacity of the sample. We don't often measure heat capacity in the pharmaceutical field, but changes in heat capacity are super important when trying to understand the glass transition in amorphous materials, as we'll return to later in the series. So, for now, remember there are two types of DSC, heat flux and power compensation, that differ in the number of furnaces. In either case, the instrument is programmed to change the temperature of sample and reference materials between two values at a constant rate. If the sample undergoes a phase transition, it will require more or less energy to change temperature than the reference, and this difference will be manifest as a peak in the DSC trace. From a peak in a DSC, we can determine the transition temperature, the area under the curve, which is the total heat change from the transition, and get information on heat capacity. In the next video, we will look at the effect of heating rate on the peaks we see in a DSC trace. So I hope you'll join me for that. If you like this video, please hit the like button and consider subscribing, because it really helps the channel. In the meantime, thank you so much for watching, and I'll see you again soon.